Good morning, New Mexico. We'll get started here in just a couple of minutes. All right. Good morning, guys. I see the chat's working. Thanks for getting on in there. All right. I think we're all set here. Hey, there's our folks from Clovis. 50 degrees doesn't sound too bad, all things considered. Angel Fire. Hey, thanks a lot for joining us, guys. Great to see everybody this morning. Nice full bench, too. Man, lots of attendees. This is fantastic. All right. Looks like my screen's showing up from what I can see on my end here. Hopefully nobody's having trouble hearing me. Good morning, Hobbs. Got a bunch of our southern New Mexico towns represented this morning. Great to see y'all. All right. Well, it is time to get started. 8 o'clock on the dot. Good morning, everybody. My name is Andre Hayen. Today I'm going to be walking you through heat pumps. I'm a member of the team with Shums Coda Associates. I've taught classes down in Clovis, down in a couple of places, Hobbs. Oh, there is the wonderful, incomparable Hope Medina. Good morning.
Morning.
Good to see you. All right. Well, we were just kicking off. We were just getting started here. So, we'll go ahead and jump into things. So, today we are talking about heat pumps. Now, heat pumps are a useful and interesting piece of technology, and I'm going to call it exactly that. It is a piece of technology and it operates on a certain scientific principle. And so, we're going to take a look at what that means today. We're going to spend a little bit of time on the building science behind it. We're going to talk about how it works from physical principles, a little bit about the history behind heat pumps themselves. And then we're going to talk about the code requirements for them. So you're going to get the down low on where it comes from, how it came to be, and then we're going to end on how you use it every day with the code if you're starting to see these things or getting more of an interest in them. So you can see here that we have a system that looks a bit complex, but in all reality is kind of a simple process. We got air coming in, we have it passing through some things. We see some copper coils in there, right? We see some specific boxes that are letting heat or letting air in certain ways. And then it's getting filtered into the rest of a duct system here. And you can tell that we have both intake and exhaust happening. You see those red arrows on the top and those blue arrows coming into the bottom. And what that really is trying to dictate to you is that in order to run a heat pump effectively, we have to control the direction of air. And that's going to be a really important sort of concept, regardless of the type of heat pump that we use. We're really capturing this principle of using air in very specific means, and that's what it's trying to do. So let's get started with the science behind them. Now, what is the science that allows them to work? Well, I'm going to take everybody back to high school physics. The first law of thermodynamics. This says that energy cannot be created or destroyed. And so we have this principle that whatever we have energy in, we get energy out of a system, and we get waste. So, for example, we get a furnace, right? Let's take a look at a furnace. 100,000 BTUs of input. That's a really common size or a really simple math size for a furnace to look at. And we're going to say it's 90% efficient. So an AFUE of 90%. So it's a relatively relatively high efficient furnace. What that really means is that we get 90,000 BTUs of output, and 10,000 BTUs are going to be imperfect combustion in that system. That's going to be system waste, effectively. That's going to be heating the heat exchanger. That's going to be the temperature rise differential, the things that we can't get full combustion and full heat out of. And so when we can't do that, hope you look confused. What's going on? Oh, I can't hear
Uh,
you.
oh, sorry, my screen just went crazy and I was just trying to fix it. Don't
Oh,
worry
okay.
about my face. Sorry.
No, no, you're good. You're good. Just was getting worried you couldn't see my screen or something. Yeah, I was worried I was having issues on my end. So, okay. All right. So you have this 100,000 BTU furnace, 90% efficient. That means that some part of that energy is going to be imperfect, right? So that's condensate, that's flue gases, like this captures here. And we move on to the second law of thermodynamics, right? So we have this already kind of existing principle that heating systems are going to, by definition, be imperfect. Then we say heat moves from high temperature regions to cold temperature regions, or to put it more simply, heat wants to move to the cold places in the universe. All energy wants to flow until it's evenly dispersed throughout the entire universe, right? So when something's hot, that heat wants to get to the cold place for it. Basically, the excited molecules, whether that's in air, right? The excited molecules are bouncing around a lot faster. They want room to be able to move around. And the cold molecules, less excitement, right? And so that means that that heat wants to move, that energy wants to flow to those cold spaces. So no reaction is going to be 100% complete, right? We already captured that in the first principle. That's why we always have that heat waste or energy loss that's created in the process of heating something. And whenever energy is transferred or transformed, more of it is typically wasted in that process. Now, there is one thing we have to take a quick digression for, which is important because we're talking about heating spaces. And so, what's the difference between temperature and heat? Well, heat in physics, especially, and in what we do here with building science, is a form of energy. And we're measuring that in one body system to another. But temperature is an internal measure of a system, right? So when you take your temperature, when you put a thermometer in your mouth, right, that's taking your internal temperature. It is letting you know what that is. Whereas the thermostat in your house is giving you the internal temperature of your house. You may also have one that picks up the external temperature, right? So that way you have that relative disposition between hot and cold. But typically speaking, that's what we're working with when we talk about temperatures. What is it inside of this space or this closed system? So we know the volume that we're trying to heat, right? Same thing if we're measuring, say, if you put a thermometer in a brisket, right? If you are smoking some meat that day and you're making good lunch, right? You're having the carne asada, right? You put the thermometer in, you're getting the heat of what's inside of maybe that foil pack or that butcher's wrap, right? You're getting that internal temperature. And that's going to measure how fast those molecules are traveling in that system. Remember, that's excitement. Excitement is heat in that physics principle, right? So if thermal energy increases, the random motion of atoms, that excitement, tends to go up, right? That's what we're seeing with that. So on heat transfer, what we're talking about is moving heat between one place and another place. And so things don't have to be hot to have energy. They just have to be relatively hotter than the other side, right? If there's a hot and a cold, that means that we can transfer heat or transfer energy from one place to another because of the relative disposition between those two temperatures. So here we have, say, a stick of metal, something that's going to transmit or allow the transduction of heat from one place to another. And we put it over a little Zippo lighter, right? If I hold whatever it is, right? Or maybe a better example is holding a cast iron pan over a campfire, right? For a while, it's just going to heat up the contents of the pan, but eventually that heat is going to make its way into the handle, and I better have a towel or, one of those little silicone kind of wrap things for the handle. Otherwise, it's going to burn my hand. So as that heat wants to move, we can take advantage of that principle. Now, when we look at the concepts of how we heat a home, we need to also produce or parse out these two ideas of sensible heat and latent heat, because that's also going to be one of the major principles we take advantage of with a heat pump. Sensible and latent heat are describing two different ways that energy is released or absorbed by a surface. Well, what does that really mean? Sensible heat means heat changes with no change in phase and state. What does that mean? Changes in phase and state. Well, the next answer has that, right? That can be things like changing from a solid to a liquid or a gas, right? So here is one of those examples. If I take dry ice and I open a container of dry ice in 70-degree temperature, what happens? It immediately turns from a solid to a gas. That's how we're able to, especially if you drop it in water or something like that, that's going to cause it to melt faster. That's how we get those cool sort of fog machine, kind of sort of expansions of gas. That's exactly what we're taking advantage of in that process is latent phase state. And we can see that, with that phase state change because we see literally the boiling happen. So if you ever dropped dry ice into a bucket of water, you get the immediate boiling effect. You get little particles of water shooting off all the time because so much gas is being created so quickly. Now, for the chat, can anyone think of anything else besides dry ice that moves directly from a solid to a gas without stopping in a liquid state? Take your time, toss an answer in the chat if you have an example. Snow typically, right, would melt. We might have an example there where we go from ice to water to then water vapor or gas, right? Good guess, though. Appreciate you jumping in, Richard. Uh, other examples you might have. There's a weird one out there. This process is called sublimation specifically. Wood is actually an example, right? There's no such thing as liquid wood. Yeah, also called sublimation. Yeah, absolutely. Yeah. So that is, yeah, that's an example of something changing phase states in a really, really violent reaction. And so we can see that from a chemical standpoint, we take advantage of that difference all of the time. We use that in a number of different things, chemically. It's really important to us. And here we're going to use a little bit of the same thing because in heat pumps, we rely on refrigerants. Refrigerants do a lot of the load for us here. And what we're going to see is the process of taking a liquid refrigerant and running it through a process where we're going to take advantage of its change in phase state, the latent heat change, to then turn into a gas and then back into a liquid again. That's really important to the concept of running a heat pump. So in order to stand all this, we really have to take advantage of these core principles. So we're going to delve in a little bit deeper. Sensible heat can be measured by a thermometer. Sensible heat is something if you've been getting manual J's and D's or getting more involved in your mechanical system design, right? That's usually captured in those documents themselves. That's telling you basically how many BTUs it's going to take to change the temperature in the space, heat the space to a certain desired temperature, usually that 75 or 70 degrees, depending on kind of your setup in the manual J process, but usually right around there. So that's heat carried by the air or air temperature. We're not making a jump between phase states. We're not going from a liquid to a gas or a solid to a gas. And this is described in our heat load calculations, like I was saying, and it can be captured from a bunch of different sources. We can talk about things like sunlight entering the home. We can talk about the insulated thermal envelope. That's going to give us the boundary in which we're going to sensibly heat that area, that space. Air infiltration and exfiltration, that's going to give us a better idea of how much of that heat we are losing, right? Maybe passing through air leakage points, maybe just ambiently needing to be reheated. Lighting creates sensible heat. That's why it's calculated into the mechanical system in your manual J. Appliances, appliance motors, those also have sensible heat loads. And occupants. Occupants also add sensible heat load. Excuse me. Latent heat is taking advantage of that phase state principle, moving from solid to liquid, liquid vapor. These are things like heat pumps and air conditioners that take advantage of refrigerant principles. And what that refrigerant is always doing is moving in phase state change. And the better those chemicals have gotten at being able to do that makes a huge difference in its ability to be able to be effective as a refrigerant for this purpose. So the better it gets at being able to flip quickly between those states, the more we can take advantage of it, which is a really important principle for us. So, when we're talking about this for the state of New Mexico, we are talking about two codes that you're going to work with here. You're going to talk with the 2021 IECC, that is your standard energy code, right? You are also on the 2021 Uniform Mechanical Code. And so, when those two are aligned, that's the principles or the documents that we're going to be putting together. That's what you guys have adopted as a state. So, that's what we're going to be pointing to for your code requirements associated with these. Now, the IECC is going to typically dictate the things of how efficient things need to be. and set some requirements about the design parameters to demonstrate that efficiency. The Uniform Mechanical Code is going to give you the provisions associated with making sure that particular installation is safe and in accordance with good practices from a mechanical standpoint. So efficiency on one side, mechanical installation safety requirements on the other. Great question, Richard. The slides being available. Yeah, I can do at the end of this. For anybody else that wants the slides, just let me know, put it in the chat that you're requesting them. I'll pull the list out of this and I can send a follow-up email. I can make this into a PDF handout afterwards and send those out to you. So absolutely happy to. So why do we spend all this time? Thank you, Jerry. Why do you spend all this time in the design of HVAC systems? Well, there's a number of good reasons. Number one, sizing the equipment. Um, oh, thank you very much, Hope. It looks like Hope's going to drop it in the chat for us and save us that, so you'll be able to download it. If that doesn't work for you, once again, just let us know in the chat and we'll get it over to you. So, why do we go through this process? Why do we do this design of HVAC in buildings? Number one, the sizing of equipment. If equipment's oversized, that means that it does not work properly. Oh, not seeing the questions, Ken. Let's see here. Not seeing the slides or not seeing the stuff put in the chat? Hmm. Okay. Hope, if you could get with Ken there and give him a hand, because he's looking for something in the chat here, I think, but it's not showing up for him.
No problem.
Thank you very much. I appreciate you. Um, so if equipment's oversized, what it does is it ends up short cycling, which ultimately does a couple of things. It means that it's not going to work as efficiently and effectively over the entire size of the building or the life of the building. It's also not going to work really great for the equipment in and of itself. If it's not running through full cycle, that means that we're putting demand on the system that it may not actually need to be there. So it's not going to perform as designed. So improving comfort. Comfortable occupants are safer occupants. So when people are involved in buildings, right? When people are occupying buildings, the one thing we can count on more than anything else is that they're going to make themselves comfortable regardless of what it takes to do that. And what I mean by that is for instance, I worked at a building, a big commercial building that had terrible, terrible heating. This was where I was a code official. And when I would walk by my permit techs midwinter, every single one of them had a blanket at their desk, had a space heater under their desk, had maybe an additional space heater on top of their desk. And then there was also an air purifier. They had fans running. Basically, this is that iconic, everything is daisy chained into all of the different, all of the different power strips that they have there. Um, and so this is the places where things get risky, where people start making decisions that because they need to be in an office for 8 hours or they need to be at home and they need to keep their kids warm, these are the instances where we hear about people making terrible decisions, right? These are the things like trying to heat your home from your gas stove, right? These are the kinds of things that people will do if they are uncomfortable. So the more that we can guarantee that their overall system is going to make them comfortable, it is directly, in my mind, a function of ensuring that they are going to be relatively safe. Is that going to work for everybody? No, no. But we also know that when people are desperate to be warm, they're willing to do pretty crazy or sometimes very dumb things in order to achieve that. It's just the reality of it. Beyond that, it does reduce energy consumption as well, and that's a huge part of why we're here. Good design mechanical systems ultimately relieve the overall energy use and waste of a bad system and try to ensure that what we have is right sized for the building that we're using it for. And all of that is going to protect the building over its usable life because when a building's air sealed properly and it doesn't rely on things like additional supplemental heating systems like a plug-in space heater, things like that. It's going to help ensure that that building is more protected from things like occupant fire, occupant mistakes, things like that. It also allows us to be able to control moisture and air infiltration because we're really picking the times where we're going to control letting that air in and to run it through things like filters and more designed systems so we can really accommodate any sort of configuration that best fits the needs of that building. So that's why we go through all this process. That's the value behind it. And so now we're going to move on to the heat pump themselves. We're done with the science section. We're done with high school physics. Take a moment here. Does anybody have any questions about this section and talking about sort of like the purpose, the reason, and the science that backs up heat pumps? I did see that the slides made it into the chat, so if anybody has trouble downloading those, like I said, just let us know. And thank you very much, Hope.
It can be useful every once in a while.
Every day, what are you talking about every once in a while? We won't hold it against you that you're a Packers fan, but otherwise, you're batting 1,000. All right. So let's jump into heat pumps themselves. First question for y'all. How old do you think heat pumps are? I would love if people wanted to jump into the chat on this one. Tell us how old you think heat pumps are. Would love to hear it. 100 years. Okay. 500 years, 20 years. Getting all kinds of different answers. Running the full gamut. There's some really, really interesting ones here. Keep going. What else you guys got? Minimum 1800. Okay, so we're going by a date on that one instead of just number of years. Totally. 150. Okay.
Maybe
All right.
Richard was saying 1,800 years. I mean, the energy code's been around a long time, back with ancient Romans. So.
Oh, are we going to talk about hypocaust systems today, Hope?
No, we are talking about heat pumps.
Okay. All right. 60 years. Geothermal count? Oh yeah. Okay. Geothermal heat pumps. That is conceptually a much older concept, Michael. Absolutely. I guess I am talking more about like modern refrigerant ones, but yeah, that is a very good point. All right, we'll go ahead and get to the answer. More than 150 years for just refrigerant style heat pumps. So, for just what we are talking about today, this more modern convention has actually existed for more than 150 years. Um, Hey, there you got it. And Randy's beating me to the punch. He's stealing my thunder over here. Yeah, we date back the principle with artificial refrigeration to 1748. This actually marks a really landmark discovery by the time we get to the 1830s, because for those of you that might be history enthusiasts, you know that the United States could never have been the United States without the railways, right? And the railways helped deliver that promise of growth and commerce through refrigerated cars, which started to be picked up in the early 1800s, about 1830, 1850. So we're starting to get the first types of refrigeration in our ability to be able to move things like produce, create ice in cities, right? Those are huge discoveries that really change the way that we integrate with the agricultural sector, right? How we're able to build bigger and bigger cities and put agriculture sectors further and further away. Is because we're then able to move those goods without them spoiling longer and longer distances. It is a crucial time period for the growth of the United States during that. And so there's a lot of scientific discovery happening here. There's a lot of interest in this from corporate giants at the time that are really trying to build in all the things that this could end up being as we industrialize, that process of bringing agricultural goods to market. And we see the fruition of the Industrial Revolution at the same time. So this is just a really fascinating time of discovery. 1852, Lord Kelvin describes the theory underlying a heat pump, basically what we talked about earlier today. So it takes Lord Kelvin and his scientific mind and a lot of other contemporaries with him, the process of developing and working with the principles of thermodynamics to a place where they could recognize and discover that through heat transfer, they could actually regulate the heat in a space or in a structure. And this becomes the underlying principle of a heat pump. By 1855, we start building, as was pointed out by Randy, 1855, 1857, we start developing the actual first commercial size heat pumps. And then 1945, we're building water source heat pumps, and the plurality, the use of that technology is starting to become more and more expanded. And by 1983, In Finland, they're building heat pumps that then can handle the loads basically for whole commercial uses, whole city uses, things like that. So now we're really on to, the using technology to almost like unbridled, unprecedented use. So this is a little bit of what some of those things have looked like. On the top there, we see a pretty modern Samsung unit, right? We see a carrier unit that has seen some better days. Just below that, Mitsubishi one. We see one in a mechanical courtyard on top of a commercial building out here, and we see a number actually stacked up smaller units. Let me see if I can get this to do. There it is. We see smaller units also hanging out. But the one on the left here that I want to point to is one of the oldest ones. This is from History of Heat Pumps from the Swiss Federation. So I had to go to one of their government sites over there for that photo credit top left. The rest of these, the team and us, we took ourselves, but that one top left is one of the oldest working units. And so it's like one of those things when they talk about the original like IBM computers that NASA was using, where they took up like an entire room in a commercial building, or a whole section of that building. These heat pumps were kind of the same size. These were massive when they were first being built, and now you can see all of that technology or all of that principle is now condensed into something as small as that little Samsung guy over there. But the reality is that that is the birthplace from where this came from. And that was also part of the problem with this, is that the technology required lots of space, it was noisy, and so that was part of the reason that it didn't have much allure. It wasn't until the technology's come along a long way that now we've hit a point where people are much more amenable to using these regularly. And I see we had a question in the chat here. From my understanding, let's see here. Sizing per cooling load manual J should not exceed 25% the cooling load required. For plan review purposes, should sizes over that 25% be disapproved? Well, typically speaking, the answer to that would be yes. And so, Stuart, you offer really good insight on that. So typically for heating purposes, we can size up to about 40%. That's what Manual J says, right? 140% of additional load for a typical Manual J. And remember, Manual J is specific to residential loads, right? The process for doing commercial loads looks really different, and I would say that the parameters are a little bit more loose there because sometimes those equipment pieces are kind of hard to size or kind of hard to get right. There are some things like manual N you can do for limited low-rise applications, which is again an ACA manual, but it's for some specific commercial uses that kind of give the same thing. But that's kind of a best practice thing. It doesn't show up in the code. That's just, one of the options out there. So saying all of that. Yes, if we go beyond the parameters of the manual J, then we should at least have an explanation as to what that is. So Hope's jumping in saying it's 15% that is allowed to be oversized. Now, if I'm not mistaken, there are some recommendations from manufacturers basically that if there is no other piece of equipment that's going to fit that need, there is some trigger point about 25% if I remember correctly. And Hope, if you want to jump in, or certainly Stuart, you can as well. I'm pretty sure there is some trigger point at 25% that matters if you can't find the right piece of equipment within that 15%.
Yeah, there is the
Mhm.
15% is kind of the catch-all. If you
Hmm.
go into Manual J, there are a couple of, I would say, quote unquote, exceptions that it does allow for certain
Yep.
types of equipment that
Yeah.
they
And
do
Stuart
get to
said for
go up
certain
to the
climates.
25%. Yeah. So there
Hmm.
there is it's 15% basically unless you fall under these certain parameters to have it a little bit above. But
That's okay. Yeah. So, yes, and so you are correct. The guardrails exist for good reason. Basically, when you're approaching that 25%, or 15%, depending on what's allowed based on climate zone at a manual J, you are approaching a point at which the next size piece of equipment probably makes more sense for that building. So that's part of the parameters for that, and then also making sure that it's not going to do the things we were talking about earlier, short cycle, not run efficiently, those sorts of things. So that's part of the reason that we have the limitations that we do for those sorts of things. If your equipment is not fitting that, then yes, you should call that to the mat. and maybe encourage somebody to look at a different manufacturer that might have something that's better suited. Now, heat pumps, because you get the variety of different applications, right? You get standard air source heat pumps, you get mini splits, you get a lot of different options. Oftentimes, what I see is a lot more use of piecemealing the different components together for what they want to get a pretty precise calculation on the load that they want to end up with, right? Because they can get down to, 8,000, 7,000 BTUs of additional load. They can get fairly precise with that depending on how many they want to put in a system, how many rooms they want to specifically have, maybe their own mini split system, or things like that. The other important thing to keep in mind is whether or not they're being added as supplemental. So you can have a typical like furnace and AC, and then you can also have a heat pump that's carrying the load when it can the majority of the time. And then when your loads stretch beyond the capacity of that heat pump, that can be the point at which a more traditional system maybe picks up some of that load as well. So it's important to think about this as a flexibility tool, but also something that still needs to meet those minimum efficiencies. Great question and really good place to kind of take a moment and stop and talk about the concept behind this. So, why haven't we just all used heat pumps? If they're just the greatest technology ever, why didn't we? Well, a few reasons. Number one, we've typically had cheap fuels in the United States. For those that are on this call that are probably older than me and old enough to remember these days, right? I unfortunately cannot say that. But the 1970s oil crisis, the OPEC crisis, really cued in a question about the ability to get cheap fuels. I would say that today, with the current war in Iran, we are obviously seeing a lot of the same questions of how available certain fuels are going to be, and sometimes the impacts of that, right? That's going to be one of the outcomes that we're going to see today. But again, it's going to raise this question of how do we do things cheaply, right? They were also relatively loud. They got a lot quieter circa 2000-ish, but historically speaking, these were loud pieces of equipment and relatively big pieces of equipment. There were also climate limitations on these, and that came from the availability to find refrigerants that would work in cold climates, and also the efficiency of the technology themselves. That's really developed and grown in recent years. And so now we have specifically USDOE and Energy Star, right? And those are federal programs that regulate that level of efficiency, have targeted cold climate use and the applicability of cold climate use. And encourage manufacturers to take strides in that space to develop equipment that specifically addresses cool climates, cold climates. So, why is there such an emphasis on heat pumps today? Well, overall, heating buildings with fossil fuels accounts for about 10% of overall global emissions, which a lot of communities and a lot of nations are targeting. And they're trying to encourage people to make other choices with the way that they heat their buildings, right? We saw that with the Inflation Reduction Act, which added a 30% tax credit for heat pumps. Some of these have gone away, some of them are still in existence, some of them might be supplemented by local programs. It's important that you at least keep a finger on the pulse. I know we get a mix of folks here that are designers, installers, and then code officials as well. And knowing, what pieces of equipment are getting incentivized in order to be able to save somebody some money and to get maybe some tax benefits and things like that. There's no getting around it. Whenever we add a tax benefit to something, that is encouragement by definition, right? Through some sort of government program to incentivize the use of a particular technology or something like that. So keeping a pulse on, where that is kind of makes sense because it can help you kind of figure out what types of systems may be incentivized, right? Heat pumps, because of the way that they operate, can meet much higher efficiencies than we were talking about earlier. Earlier, we were talking about using a conventional furnace, 100,000 BTUs, 90% efficient, means the best it can ever do is 90,000 BTUs. That is in a perfect world with, the perfect amount of oxygen ratio, things like that. And we do know that as we go up in elevation, for instance, that changes. So my first car, I got to rebuild myself. It was a 66 Mustang, but don't get too excited. It was the inline six, so it was a pooch. It was slow, single barrel carburetor, right? But for anyone that's worked on a car that old, you know that you've had to do things like rejet carburetors, right? Work with certain components in it to make sure that you're getting the right oxygen and airflow mixture. And it would run terribly above certain elevations because I live in Colorado where you would take that up into the mountains and it would start to really sputter, cough a bit along the way. That's because the air got thin and couldn't run properly. Well, mechanical systems also do a lot of the same thing when they're fuel gas oriented as well. So your mechanical system is designed at sea level, and then as it's brought up in height, right, in elevation, that changes its efficiency process. That will account for some deration in manual JD&S. A lot of manufacturers will publish specific data for that and say, for every 1,000 feet, maybe above 3,000 or 4,000 feet in elevation, we want you to derate efficiency by 2%, 4%. You know, they'll have some metric for you there. ACA Manual J also has a more generic metric if your manufacturer doesn't supply one. But that's one of the advantages there is if you have more and more elevation, that means systems like this might be able to run more efficiently. But also, just based on its principle, it can run 300 or 400% efficiency because it's not going to create heat. It's going to move heat because it's not going to be creating heat in forms of electricity. For a space heater, by definition, so if we're looking at an electrical system that's just going to use electric resistance heating, the best it can be is 100% efficient. Most aren't 100% efficient exactly. They're 95%, 96%, things like that. Because, like we talked about, any system that's creating heat has to always have some form of waste byproduct with it, right? That's the second law of thermodynamics. Nothing is going to be perfect in that process. There's going to be some heat lost in the creation of heat. And that's just it. Heat pumps don't do that. What they do is they move energy. They don't create energy or generate energy. So let's talk about the principle about how they do that. What's the principle at work? Well, we're taking air in from basically temperature differential. We're using the opportunity to say, okay, it is colder or hotter on one side of this system. And so this really emphasizes the value of the thermal envelope. Without a good thermal envelope, there is not a barrier to create a difference in temperature differential for a heat pump to take advantage of. So for heat pumps to work well, we need good air sealing, we need good thermal envelope, we need good basics when it comes to energy code enforcement in order to ensure that the system is going to get the best life it possibly can. But what it's going to do is use that outside temperature differential. So if it's hot on the outside, cool on the inside, and we want to, say, for instance, keep it cool on the inside, what we're going to do is take that energy and move it through this process of evaporation, compression, condensation, and expansion. That's all referring to the refrigerant in the design of the system from heat source to heat sink. And using that, we're going to be able to move that heat to where we want it to be. Now, there are multiple ways to be able to do this. We can do things like an air source heat pump, which is going to use a compressor and two coils and a reversing valve. Now, the reversing valve is probably the most important part of this because that's going to let it work in both directions effectively. What that means is it's going to be able to move the hot from outside to inside when we want it, and then the cold from outside to inside when we want it. So that's how it's able to do both cooling and heating is by taking advantage of this reversing valve principle. And so we can see sort of the inner workings that we saw earlier in that first picture. We can see that unit sitting outside here. So what does that really mean? Well, here is a really good breakdown. The outside coil is going to remove heat from air and evaporates into a gas. That's where that refrigerant is going to do that latent phase state change. That's that first step. The indoor coil is going to release the heat back from the refrigerant as it condenses back into a liquid. So again, we're taking advantage of that latency principle. And then the reversing valve is going to swap it from heating to cooling or cooling to heating. It's also going to assist for the defrosting process when the outside coil is in winter. So what that means is, hey, the refrigerant can only operate at a certain temperature sort of curve. If we go beyond that, oftentimes what we have to do is put this thing in a defrost mode. What that's going to mean is there might be some supplemental electric resistance heating or things like that that's going to pre-warm some of that coil so that way the refrigerant can better do its job. So what it's going to take advantage of is the outside coil moving that air. Let me turn on my little, there it goes. That outside coil is going to move and absorb the refrigerant, or excuse me, the air is going to move through that coil, and the refrigerant is going to absorb that heat, and then it's going to boil to a vapor. It's going to move through this process, through the compressor, and into the inside of the home, where this coil is going to release that heat into the air, and this is going to return into a liquid state. So you notice that each step along the way, we're really reliant on this refrigerant able to do its job. And we see that we have two sort of settings here. We have this high pressure, high temperature liquid. Then as we move through this process, it moves back to a low temperature, low pressure liquid as a refrigerant. So this is the principle that's at work here for us to be able to take advantage of. So when we run a heat pump, we're not converting electricity directly into heat. We're just running a pump with a refrigerant cycle. And that's how it can be so efficient, is because the bigger the differential that the refrigerant is able to take advantage of, the more effective this can be. So on average, an air source heat pump uses about the same amount of current as a refrigerator, which isn't that much when we think about other heating appliances. You can have smaller systems that draw as little as 10 amps. You can have larger systems upwards of 20 or 30 amp currents as well. It just depends on the size of the pump and the size of the process that we're going to use it for. Ground source heat pumps have even more control over the temperature disparity because what we're going to do is basically dig down and drill either a little well or a series of loops, right, for this closed loop system. But what that's going to do is take advantage of the ground temperature, right? The ground temperature is always really stable, right? You go down a couple of feet into the dirt, and that temperature is pretty much always going to be the same no matter what's going on, whether it's snowing or whether it is blistering hot, right? That temperature is going to be basically accountable. And so we know that we can take advantage of that whether we're heating or cooling a home. The problem or the difficulties with this is obviously you need the space to be able to do it. It's also more expensive to be able to put in because we need to go and drill down these loops. We need to make sure that this entire system gets put in. But it's really effective at being able to take advantage of a predictable temperature differential. So they have open or closed loop systems. That's that well on the left where we're drilling down and then these are filled with water. And then the closed loop system is going to be exactly that, just loops ran through the ground themselves. The piping can be in ground or in water, like we were just saying. And then that heat exchanger is still taking advantage of the same principle of running that refrigerant through the process, using a loop on the inside of the building where that heat or that cooling is going to be pushed through to the rest of the building. And then that refrigerant cycle is going to continue back and forth through this process. So, generally speaking, these are going to be more efficient than air source heat pumps because, again, you're very predictable. They cost more to install, but they have a lower operating cost and they can be used in more extreme climates because they're more effective. So, we've talked a little bit about these two basics. So, what does a cold climate heat pump mean exactly? What do we have there? Well, cold climate heat pumps really mean a basic thing here that's they're able to perform at -5 degrees. Now, it's a simple concept, but you can understand now from the context that we've added through our class today why that's such an important concept is because that system probably has a couple of different features to it that other systems didn't need to. Things like supplemental heat for defrost cycles, things like certain refrigerants that are able to perform at such a low temperature. But every system, and this is what I really want to drive home, right? A lot of people look at that and say, well, if it's more than -10 outside, that means that it doesn't work. Well, kind of. It means that it won't work as well, but neither is any other system that we're putting in. So if you've done mechanical systems before, for instance, looking at a manual J, you know that there's a temperature differential that every gas-fired furnace is designed for, where the outside air coming in needs to be heated in order to be able to run through the heat exchanger. And once it gets to a certain point where it is really, really cold, there is a same thing. There is a curve and a drop off where the efficiency of that system will be harmed by how effective that is. Now, it'll still operate. At the difference there in my first house was this 55 brick ranch. Lots of air leakage, pretty cold in the winter. And when my furnace was running, it was running pretty much all winter, or excuse me, all day when it was like -20 outside, -10, things like that. It would still heat the house, but it took more energy to be able to do that. It wasn't running quite as efficiently, and you could tell it really like the kickoff would only last for a minute or two, and then it would, come back on. Well, similarly, every system has a certain curve where it's going to be performing its most adequately, and then outside of that, it's going to have diminished returns. And that's also very evident with heat pumps as well. So every system fails from this. It is also a point at which, you want to make sure that the prescribed system for that heat pump fits the needs of the climate that you're putting in. So that is really meaningful to make sure that it can be used for as much of the year as possible. So, the unique power of refrigerants. Again, we are really taking advantage of this principle. Refrigerants are really easy to manipulate. There's all kinds of different refrigerants out there. That is a space chemically that's still growing. They're making new and new refrigerants. Some of them are flammable. That's one of the things that we have to keep in mind. But they typically have low boiling points and then can quickly transform from that liquid to that vapor and repeatedly phase change without kind of exhausting the abilities of that particular chemical to do it. And when they go through that phase change state, that's when that latency occurs, where we're able to take advantage of that. So today, R410A is typically one of the most widely used refrigerants in heat pumps. It's got a lower boiling point than R22, meaning it can absorb more cold or more heat at those temperatures, boosting its efficiency, and it's less harmful to the ozone layer. One of the other things that we've obviously been worried about with different refrigerants and different aerosols out there. There's plenty of others like R32, R260. I think like R34 is just propane. So yeah, like some of these are just flammable chemicals, but they're able to also perform this task. And so that's part of the reason that we want to pay attention to what it is that we're putting in these buildings and simultaneously its efficiency to be part of the system as a heat pump. And so what it's doing, right, and I really want to drive this home, this is where I was saying that it really matters how effective the thermal envelope is and how efficient of a thermal envelope we've created because we have to move energy across a boundary. The more efficient that boundary is at separating the outside from the inside, the better the system is going to be at taking advantage of the refrigeration cycle and ultimately keeping the temperature where we want it to be. So we can see here that this expansion valve setup, right, this whole thing right here is the refrigerant cycle for a heat pump. So we've got the outside coil, we have the inside coil. I have that backwards, I'm sorry. We have the inside coil, we have the outside coil. This blue line right here represents literally the threshold for the house itself, right, or the building. This represents the point at which this is either entering or exiting the inside or outside of the building. But this process allows us to take advantage of moving heat. And so, how do we create that effective boundary to be that blue line there? How do we do that effectively? Well, the three parts to that that really matter are our air barrier, our vapor retarder, and our insulation. And the continuity of that system as a whole is part of what makes the system able to be run. So that also allows us to control the airflow, the dust, the debris. It allows us to build that durability that we talked about earlier. But ultimately, and I am sorry, I don't know why this when this slide came in that kind of like overlapped over the insulation here in the green in the Venn diagram. But air barrier, insulation, and vapor retarder are the three components that we have to have in order to be able to make a wall system that's going to create that separation that we really need. And so the new technologies being associated in the space really have been growing. They're able to get more refrigerant into higher pressure using less power. The pumps are getting better. Variable speed compressors mean that we don't just run the system in a on-off, but now we're able to ramp up their power up and down. So that's a major change to this. So really, the technology has had some substantial improvements recently that again are packing in more and more depth to these systems in smaller and smaller packages. So, some of the basic types of systems that we can see here, ducted, where it's going to be tied into a more conventional ducting system and maybe also a furnace and AC system. Like I said, there's plenty of systems out there where they take advantage of a heat pump for the vast majority of their load, but they have a more traditional system in case the loads cannot be supported by that heat pump. You can do mini split or ductless systems. You can do ventilation combined systems, air to water heat pumps, ground to air or ground to water. There are a number of different mixed systems that you can take advantage of through heat pumps because now that we've been through this, you can see that it's capturing the same principle. Where can I capture a temperature differential and run it through a refrigerant cycle? And that's really about it. So, federal efficiency ratings. Never forget that we have made a jump as of the very tail end of last year to now. Um, We have gone from EER, SEER, and HSPF to the 2 series of those, but it doesn't change the numerical value that needs to be associated with that. It's not as though the EER2 jump means that we change that number out of the energy code for any reason. We can go through each of these, but energy efficiency ratio is going to be the heat removed, measured in BTUs through electric power used to remove the heat. So that's basically going to be an efficiency rating for a heat pump here. And you can see that ratio being put out here for you, that it's heat removed in BTUs over the energy used for itself. The seasonal appropriation for this calculates this over a cooling season. So it looks at it to say, okay, over the curve of hot to cold temperatures, how's that ratio going to be impacted? So we can do this as sort of like a slice in time. We can look at this over the course of an entire season and say, okay, how effective is it in the climate that it's going to be sitting in? That's what we're taking advantage of with the SEER concept, but it's the same calculation, just done over a longer series of time. Remember, the best we can shoot for on baseboards, 100% efficient, right? Furnaces, that's the best we can ever hope for. And remember, that hope is just that. It's a hope. We can't really ever get to that space. We can't land the plane at 100% because the first law and second law of thermodynamics say, hey, that doesn't work that way. But with heat pumps, they can be over 100% efficient. We also get this other one here called the heating season performance ratio, and that's again going to be the heat provided over the watts and hours used in order to provide that heat. So it's a very similar sort of ratio, but HSPF specifically refers to heating. So our previous one for SEER, we're looking at cooling. Now we're looking at heating. That leads us to coefficient of performance. Which is the ratio of heat created to the electricity required. So here we have it calculated in BTUs. That's the difference there when we get to coefficient of performance, is that we're not looking at this in terms of watts, we're looking at this in total amount of BTUs. So in order to be able to process whether or not that system is efficient, we should know a little bit about the way that we are measuring those efficiencies effectively. So remember, if there's any take home you have out of this without proper air sealing, it is really hard to get this equipment to work properly. That's why when somebody is looking at installing one of these, maybe as a retrofit, it's really prudent to look at things like air sealing when you do it. If you can take advantage of that and make some air sealing improvements to the building, it may pay better dividends than even adding some insulation in that building, depending on how you need it to perform. The sizing is going to be going through the same process. So that was a great point by Stuart, right? A different question can be, do we treat these differently because it's a heat pump and it's more efficient, right? It's that 300% efficient, so does it matter how it's sized? Well, yes, we still want to make sure that it's sized for the loads appropriately because if it's not for some reason, we get a couple of bad outcomes. We get incorrectly sized equipment for the use in terms of the BTUs that's supposed to provide for that particular house or that particular building. So we're going to follow the same process in manual JD&S. But that's exactly why existing buildings are going to be so difficult to address. Some of these are going to benefit from things like strip or baseboard heat in order to be able to supplement some of the additional heating that they need. So in order to regulate this, we go to C403.3, where we see our minimum efficiency tables, and we're going to kind of jump through these. We can look at kind of each one here, but you notice that our SEER, that regulates things like air conditioners, basically anything that's going to be doing cooling. It's also going to obviously regulate our heat pumps. Same thing with our HSPF, right? So that's where we're going to see these for the evaluation of whether or not the system is efficient as it needs to be. So we jump over to this table, we'll be able to see each of these in turn. These are the places that we would typically see this electrically operated air-cooled unitary heat pumps, right? So that's going to be our air source heat pump and the relevant efficiency ratings that it needs to subscribe to. Over here, we have terminal air conditioners, prepackaged single package of vertical heat pumps, room air conditioners, room air conditioned heat pumps. And we have our EER, COP, and CER. And same thing over here. We jump through that table. We just need to know exactly what type of system that we are applying to this. Here we have our water source heat pumps, for instance, right? And here we have EER and COP, right? And the difference there being it's not as affected by seasonal change for its ability to be able to provide its cooling because we're taking advantage of a predictable temperature differential in a ground source heat pump, right? Heat pump and heat recovery chiller packages, we're going to point to COP. And so remember, this is what we're taking advantage of with our SEER. We're rating basically an air conditioner or anything that's cooling, right? Anything that's a cooling appliance. We're looking at its efficiency. The higher the number, the more efficient the output is going to be. So cooling BTUs per the input per watt over a season, as that number goes up, we are more effective. This was a transition started to in 2023 for SEER2, and it basically just updated the federal standards for testing. That's one of the important things to know there. IEER is integrated energy efficiency ratio, and that's looking at the average year-long temperature for commercial systems at their different load levels, 100%, 75, 25, 50, etc. And it's equivalent to the SEER ratings for residential, but they're looking at it from a different paradigm there. So this is what applies when we're talking about our large commercial systems. HSPF, like we talked about, this is measuring the overall heating efficiency, but then the HSPF2 transition once again occurred in 2023, where they updated the federal standards and updated these to be more reflective of real usage, basically. Coefficient of performance. This is basically, once again, breaking this down. The COP of 4 means 4 delivered units of heat for 1 delivered unit of electricity. And remember, that's looking at a BTU to BTU ratio there. EER versus EER2, all of this transition 2023 and provided a more realistic testing. So really just the federal standards changed for the manufacturers and it got captured for us in this. But once again, it doesn't change the outcome number of what you're looking for in the code for these things. So if we are going to provide supplemental heat for these systems, we do need to look at C403.4.1.1, which is basically going to tell us, hey, these are going to operate, but we're going to put some limits on how the controls are going to work for this. And that's a really important concept here because we don't want things like supplemental heat or defrost to be running when we don't need to defrost the system. So these have to capture a few things. When the vapor compression cycle malfunctions, the thermostat malfunctions, um, the heat pump is operating in defrost mode, or the vapor compression cannot provide the necessary heating for the thermostat setting. It's basically saying we need to set this up so the heat pump is going to run as sort of the primary system here, and then the supplemental electric system can only be kicked on if it can't handle the load or it's having an error, right? It's having some sort of efficiency problem that's preventing it from being able to operate effectively. So that's the big stuff out of the energy code that you do need to be aware of. Mm. Comments on heat pump water heaters. Are you just looking for kind of thoughts about them, John, or are you looking for, maybe more of an in-depth look or discussion about them? Do you have maybe one showing up in your jurisdiction that you have questions about? Feel free to, jump in or other folks in the chat too. I'm interested about your questions here because that is actually kind of our last slide for the day. After that, we're just wrapping up on, what will be upcoming for the year. Okay, for code requirements here. So I do know that there are control settings, and I'm trying to think in the 21. I've been looking at the 24 quite a bit lately. In the 21 code, I know that there are control system settings that kind of run in the same vein, where we want to make sure that it's not operating with supplemental systems the same way, and we still have efficiency requirements. That really, I think, might take the cake on some of that. I would have to do a little bit of a dive on that because this was obviously set up for heating appliances specifically, not service water heating. So I could do a little bit more of a dive on that and maybe get back to you if you have any specific questions there, Joe. Are the coils the only filter of external air before the internal filter? Kenneth, Yeah, that is a great question. That can depend on whether or not it's part of a ducted system or integrated into the ventilation system, because you can run it through things like additional filters when it's integrated there. Now, if you're talking about an air source heat pump that is sort of that standalone system or a mini split, then yes, that is going to be the only system, and some of them will have integrated filter systems with the unit itself, but it depends on the configuration. So you absolutely can see instances, and especially when you get into commercial applications, right? Because you can use this in concert with a hospital setting where they're always about clean air, right? And multiple HEPA filter systems and things like that, where they're going to be filtering through their ducting along with whatever the input is for the coil. So it can be configured that way. How often are clothes supposed to be cleaned? Oh, that's a great question. That probably is specific to manufacturers, and you are absolutely correct. With dust storms that you guys have, I don't know that I have direct experience to be able to say, hey, it ought to be done this often. It will start to give you some issues on fault detection for the same reasons, right? Usually, if the coils are not clean enough, it's going to want to run in things like defrost mode at times where it shouldn't. Now, granted, by then that's kind of like the engine check engine light showing up on your car means you already have a problem. Doesn't mean that that's like the good impetus to be able to look at that, but it will, cause some issues for the system delivery to be as efficient as it should, and eventually it gets picked up on that. But I would have to say that's manufacturer specifics, and I'm not entirely sure for the conditions that you guys have, because they are so unique with the dust storms that you guys get. That actually is a really good question that I honestly don't have an answer for. But I would say checking with a manufacturer rep would probably be where I would start to try and find a good answer for that. That's a great one. Absolutely, guys. All right, we got 2 minutes left. You can see that you have a schedule of webinars coming up here. 326, you're going over mechanical equipment. You got a couple of things on fenestration, slab edge insulation, ventilation, continuous insulation. You got a good slate of weekly webinars coming up here. If you have any suggestions for things that you want to see, you can always shoot us a line. Our helpline email is right over here. Feel free to submit any code questions that you have. Anything that's going to be popping up in the near future here that you'd like to make sure gets captured in a particular training, feel free to let us know. Yes, April 8th, there will be an in-person training. I think I've got a slide on that here in a minute. But yeah, looking forward to seeing everybody. Let's see here. It's gonna have it. Oh, on Shumsco's website, we do have a hosting service now for you for all of the cool documents and stuff that we've built. So if there are resources that you were looking for, those are available right over here on Shumsco's website. So just Google shumscoda.com, or you can visit it directly. And you can see right over here, we have video resources, commercial and residential resources that you can go ahead and pick out from. There's a number of documents there that you might find interesting or useful, including a walkthrough on manual JD&S, which is obviously really pertinent to this class. So it might be something that you find interesting and want to take advantage of. At the end of this here, this is going to pop up. Please take a couple of minutes to fill this out. Let us know how we did today. Let us know other things that you might want in one of these trainings, what you guys want to hear. But we always appreciate you. We've got Hope's email right here if there's anybody that you need to get in contact with. Really enjoyed teaching you guys today. And we're getting you out right at 8 o'clock sharp. So let us know if you have any other questions, and have a great rest of your day, guys. Hey, thank you all for being here. All right, everybody. I am not seeing any additional questions coming in the chat or anything, so I'll go ahead and let you all go. Y'all have a great rest of your day.